please.
Okay, welcome everybody. You have found your way into the June edition of the University Lowbrow Astronomers meeting. I'm Charlie Nielsen, president of the club, and have been, I think, since the pterodactyls were flying around or something like that. We have a few other officers, maybe a couple online. I got to look again in some of the room. We may get reports from them later. But as tradition would have it, we have our guest speaker first in the event that that's really why you wanted to come here and you don't want to stick around for our highly engaging business meeting afterwards. So if you left afterwards, we won't take it too personally. And with that, I would like to first thank our online coordinator, Jeff, for finding our speaker for tonight. So thank you, Jeff. And our speaker is Adam Kall, who is a Youper. Adam is from Northern Michigan University, where he attended from 2014 to 2016. And if you didn't know, that is in the beautiful town in the UP of Marquette. So you can't blame him for not making an 8-hour drive to come down to see us. He earned his Bachelor of Science degrees in mathematics and in computer science at Northern Michigan. And then he went on to Elmhurst University, where he earned his master's in data science. While he was attending Northern Michigan University, he became friends with fellow undergraduates Austin and Troy Morris. They knew since their freshman orientation that they wanted to build their lives in the UP. Seeking employment after graduation led them to major national cities, New York, Philadelphia, and Chicago. But they became dissatisfied in those early careers and recognized that forming their own enterprise would allow them the opportunity to return to beautiful Marquette for the quality of life opportunities they had in their education and to provide high-skilled employment that they didn't have available to themselves. That was the beginning of Kall-Morris Incorporated. KMI is one of very few companies that are working on the removal of orbital debris. This is a problem that is already at critical mass, and as more accumulates, it's getting worse. Some of the larger pieces will collide with other pieces and produce smaller, more numerous, and harder to collect and remove pieces. KMI is developing spacecraft that can identify this debris, capture it, and bring it into an orbit that will cause re-entry and therefore burn up in the atmosphere. And they're going to aim it so that if any does come down, it's going to come down in the ocean. Tonight, Adam is with us via Zoom, as you can see, to talk to us about KMI and how they're going to help make space become a safer place. He is also asking for our input and experience and how all this junk in Earth orbit may be affecting us as amateur astronomers. So with that, I would ask if we give a warm welcome to Adam Kall.
Thank you for that. Well, welcome everyone. As was stated, I am Adam Kall. I am one of the 3 co-founders of Kall-Morris Incorporated, and my role is Director of Science. So that was a very bold title that we selected that basically encompasses all the theoreticals, everything that deals with numbers and orbital mechanics, and everything that comes right before you actually build the spacecraft. So Austin is our director of engineering. He gets to build the physical real thing, and Troy is our CEO. He gets to go talk to investors. I don't envy his job. And so for me, I get to focus on the data and focus on the science. And that's kind of what I did with this presentation, was really dived a little bit deeper into the data behind the orbital debris problem. I do talk about what our company is doing to solve it, but I saved that for later in the presentation. So first aspect, my introduction, as was stated, my multiple degrees, my previous experience with AI and machine learning. That was actually an internship in 2016 with NASA that got me started on the idea of machine learning. And the part I loved about it so much was this just practical aspect that if you gather enough data and enough examples, you can systematically draw out the correlations. You can understand what are the cause and effect relationships within this database, and basically the idea that if you gather enough data about the world, you can predict the future. We're not quite there yet, but there is a prediction of the future in one specific space, and that is space debris. Before I move on, it is important to mention that I am not the only one at the company. The company is now 20 full-time employees, and this mission would not be possible without each and every one of their contributions. So I always like to remind that while I may be the figurehead who is, stuck here talking long after office hours on a Friday, it is important to recognize that there is a whole team effort behind this mission of keeping space clear for all. So the problem, space debris growing, and it is growing at an exponential rate. When we founded the company back in 2019, I made this predictive chart. I said, okay, based on the historical trends, based on how things are going, and based on our expectations of launch cadence, I think this is the trend how it's going to go. Unfortunately, I was right. Now in 2025, we are directly online with that prediction, and we are just approaching 50,000 objects out in orbit. How is this happening and why is it kicking off now? Well, for one thing, there's been many more launches. We have hit an age of commercial space in which it is much more affordable to go into space. That was both our inspiration for starting a company and our realization of the problem we were about to encounter. When it becomes very easy to go into space, you're going to have a lot more traffic. There's also the concern of the Starlink mega constellations and the other ones that are starting to spin up now. They offer an amazing opportunity on the ground and infrastructure that can support not only the developed world, but all areas of the world with high-speed internet. But in doing so, they are cluttering our orbit, and if it's not done responsibly, it's going to cause a major problem, and already is causing a problem for activities like astronomy. But finally, and the biggest concern here is the tipping point of debris on debris collisions. This is the key thing that keeps me up at night, is not the fact that, oh, we might have an active satellite get hit by debris, or God forbid, the ISS get hit by debris. That would be terrifying, but the odds of that individual event is extremely low. What is not rare is the fact that every year we have about 20 or so debris objects run into each other, fragment, and create many more debris. So that was what the inspiration of the prediction was realizing this cascading effect, often known as Kessler syndrome, was starting to take hold, and it's important that we do something about it. Analyzing that data a little bit deeper, this is brought to us by our friends over at the European Space Agency, and they start to divvy out what is in those categories. So you will notice the bottom bar, the dark blue, that's active payloads, and you'll see that it has grown. That's Starlink. That's almost entirely Starlink, although there are many non-Starlink satellites launched every year. And so you could look at that and grow a bit confident saying, oh, good, okay, the growth is active payloads, it's not more debris, everything is fine. But I bring your attention to the white bars, the unidentified. That is the part that scares me because that is the debris objects where they are so plentiful in their orbit, we are unable to track them with accuracy to predict where they came from. We can no longer identify this piece of debris came from this Chinese launch or this US launch or this European launch. We can no longer identify that. We just have objects in space that we know that we're there, we know they're a threat, and we can't attribute where they came from or who they belong to, at least not right now, in addition to the other categories on here, which are in fact identifiable debris. So what is debris? Well, anything you put into space. As you all, I'm sure, know, the orbital mechanics of space allow you to put something up there, put a lot of effort into getting it into space in the first place, and then it kind of hangs around. Very little effort is needed once you put it up into an orbital path to stay in that orbital path, and that's fantastic. We can take a machine, give it all this advanced technology, and have it operate for 25 years, providing a key service for people on the ground. The only problem is that once that time is done, the machine has run out of its components or its components are no longer working in the way they were supposed to. Unless we do something, it's still going to be in orbit. That orbit is not a maintained feature, it is a kind of passive feature. And so you end up with the problem that all these objects here on the slide, these were all previous launches from the 80s and 90s that are still up there. These are some of the targets that KMI is considered from other customers, from government and US Space Force, as key targets that need to be removed because they pose a danger. And at one point, they were all previous missions. That turns out to actually be a key part of our business case that I'll get to later about how, since we know every object launched into orbit is going to either become debris or be deorbited, there is a possibility for operators to start paying for that deorbit from the beginning and save themselves and the world a lot of money and heartache. This is a image that we found shortly after founding the company, and it's a bit of a tacit reminder. The ball there is obviously representative of the ball that they shot at this chunk of aluminum at hypersonic speeds. Those speeds, even though they were one of the most advanced cannons here on Earth, only achieved about two-thirds of orbital speeds. And as you can see, caused quite a bit of damage to a chunk of aluminum that you would never fly in the satellite. So that's where the quote comes from. Two things you need to know. First, space debris is traveling many times faster than a bullet. And second, humans and satellites aren't bulletproof. This is not a problem that you can design around. The idea of we're going to launch satellites or spacecraft with armor to avoid this danger is just a little ludicrous. The armor would have to be so large and so vast just to protect from the smallest pieces. The statistic is that a piece of paint the size of your finger or your pinky nail has the energy of a hand grenade. And trying to defend against the millions of paint flecks that are flying around orbit is an act too far. So what we need to do is remove them before they're generated. The orbital bands that this happens, and this is just focusing on Leo. Obviously, orbit goes out to MEO and GEO and other areas, but just in Leo, there's a very physical reason for the problem existing where it does. Starting at the bottom, if you are under 100 kilometers, you're in the atmosphere. You're below the Kármán line. The atmospheric drag is very intense, and unless you're putting a lot of effort into staying there, you're not really in orbit. Either the heating is going to destroy you or you're going to run out of fuel. If you're above 100 kilometers, going up to about 500 kilometers, atmospheric drag is very significant. You're going to decay in a matter of months to a matter of a couple of years, and the ISS does orbit at 408 kilometers. This region is relatively clear of debris because it gets brought down fast enough that, kind of natural decay. It does, however, have a lot of transient debris, the debris from higher orbits or the debris from this orbit that's moving down. So while there's less static debris, it does make this region dangerous because it's harder to predict where's that debris going to be in the future. The ISS has had an increasing number of instances over the years where it's had to quickly maneuver to get out of the way of incoming debris. Above 500 kilometers, up to 800 kilometers, you still have drag. And that drag is important because if you're doing something like communications or Earth imaging, you want consistency in your orbit. So even though that drag only brings you down over the course of decades, it does impact your orbit. And so it's not ideal for missions where you need consistency in your orbital position or consistency in your altitude for taking pictures. And that's where we come to 800 to 900. This is the edge of that consistent orbital range, and it's where everybody wants to be. This is as close as you can get to the planet to take pictures and to use communications without being so close that you spend a lot of fuel and energy staying in your orbit. This is ideal real estate, and that's why we've already kind of lost it to debris. I could continue going. The higher orbits you do get into, there's more space between 1,000 and 2,000. That's where a lot of the more kind of legacy constellations like to exist. But the next chart kind of tells the story more clearly. That is the debris concentration of debris in rocket bodies by semi-major axis, which is average altitude of the orbit. And you can see that impact of the 800 to 1,000 area. That's where all the satellites wanted to be. That's where they were ideal for. But as it's filled up with debris, it's become too dangerous. It's now a region of space that has basically been handed over to debris. Now we have all these innovative startups that are raising millions from venture companies with an innovative idea of very low Earth orbit. Let's put our satellite as close to the Earth as we can put it. Yeah, there are some advantages to that. Your camera can be closer, you can take better pictures, but the real motivation has been that 800 to 1,000 is really no longer tenable as a safe place to put a new mission. So talking about some of that math of, Kessler syndrome, the chart on the left is what I was describing of that fall off, of how you can see there's a critical point of around 400 kilometers where your altitude is falling. You will deorbit within the year. It's just coming down. But as you get above that, the drag falls off exponentially. And so you end up with 500 kilometers being high enough that it takes 5 years to cross that point where you then quickly descend. And if you get to 550, it's going to be 20 years, and get to 600, you're really not coming down for a while. And so this is the problem that we face is not, oh, how do we, save the ISS? I would love to save the ISS, but it's kind of in that crazy place where everything is zipping on its way to deorbit. I have to worry about 600 and up. Those are the objects that unless we do something, unless we physically go and manipulate them in some way, they're going to be in orbit until they run into something else. The chart on the right is the statistical analysis I was talking about the growth of debris, but I've helpfully labeled the average, the low estimate, and the high estimate by the average time between collisions. This is not the average time between debris on debris. This is average time when an active satellite is hit by debris. As we get more and more debris and as there are more and more conjunction alerts, it starts to become overwhelming. You get to a point in which it's no longer practical to deal with every alert in a reasonable way. And because of exponential growth, we sail right past that point and continue going on to even more and more conjunction alerts. So it turns out this aspect of, debris runs into debris, causes more debris, runs into debris, causes more debris. It's very akin to a certain kind of reaction, a nuclear fission reaction, and the outcome is quite similar. This is a problem. We need to halt this cascade, but not for the same benefits as nuclear power, but in the same way that there are things we can do to kind of arrest this chain and to slow it down. As it turns out, minimal impact is necessary to have a big change. Oh, one more thing, talking about just some key events. If the average population of debris is bad, there are specific things we can do that are even worse. The first one is ASAT tests. Launching something into space to blow it up, the average military approach of, oh, I don't want that thing there, just blow it up. Well, you're in orbit. If you blow up one thing, it doesn't disappear, it becomes 1,000 things. And so there were a series of ASAT tests. The first one is the one that is honestly terrifying, 1958 to 1962, where we tested, what about nukes in space? There was a very small population of satellites at the time, and we wiped out more than half of them by detonating nukes in the upper atmosphere. That was also the inspiration for the Outer Space Treaty, because after doing that for a few years and generating, as you see, the helpful link, see artificial radiation belts, a terrifying title to an article. Following that, we signed the Outer Space Treaty because America, Soviet Union, and many, many other countries all came together and said, that's crazy. We can't do that anymore. Let's calm down and agree to some ground rules. Following that, we did still say, however, critical assets in space, what if we need to do something about them? So United States, 1985, does an ASAT test. Look at that altitude, 558 kilometers. Just went over it on the last slides. Those objects were up there for 20 more years. And the way that an ASAT test works, some of the pieces are going to get chucked lower and deorbit sooner, but some get chucked much higher, and they are still up there in space. The one in 2007 really ticked off people because that's 865 kilometers. Those pieces are definitely still up there. And then we had a couple more tests that tried to be more reasonable, try to be lower, but even those lower tests still generated debris that got rocketed into the higher altitudes. Those are man-made, and we should really stop doing them. Even though the deterrent of having an ASAT capability is important for countries, we really need to be better about testing them because it's just hazardous to the environment. The one on the right, the 2009 Iridium Cosmos collision, this one was not avoidable. This one was quite unfortunate. On just a random morning, as the two satellites were orbiting, the luck ran out and they crashed into each other. This event created, as it says, over 3,000 pieces of trackable debris. And I'm just going to let the video play a little bit because that one event was terrifying. That one singular event where two satellites became just debris. But then about 90 minutes later, 45 minutes later, this happens. They're on an orbit. That orbit intersected once before, and it's going to intersect again and again. And every time the debris has, this wild lottery of is it going to run into itself again and again. That is Kessler syndrome on a small scale. If instead of running into debris and making ever smaller fragments, there was an active satellite or an active installation, that is when we get into trouble of having more thousands of debris added to it and the Kessler syndrome taking over. Okay, I think that closed. There we go, full screen. Let me do the next slide. There we go. Okay, so how do we track it? Well, tracking debris is a fairly well-known problem. We had this idea back in the start of the Cold War and start of the space age, where we said, okay, we can launch things into space. We have to know if a missile's coming in. We have to know if something's flying overhead. Let's shine our radar, which is really good at finding planes, up into the sky. And as it turns out, it's very effective at finding things up in the sky because there's no hills to hide behind. There's no clouds. There's no trees. It's going to ping off things. You do get plenty of atmospheric noise, and there's a whole science to filtering it out. But if there's something overhead, and especially if it's a larger object like a satellite, there's a very good chance you're going to get a return with your radar as it pings back down. And so in the modern day, we have several private companies building these radar dishes that all day, every day, they just beam up into space and catch anything that's running through its beam. On the left here, you have a picture of me in Austin down in New Zealand at the Secure World Foundation Debris Summit as we went to the Leo Labs installation. That was a fun journey, but those smiles are hiding the 3 hour bus ride we had to take to get out to the boonies to go see that installation. But still, very cool experience. Another way to track debris is what you all do with your astronomy when you're looking up at the sky and you get that annoying streak through your long exposure picture of an object coming through. Most of the time, that's probably a known object. And so you can go to heavensabove.com and you can plug in your information and it'll tell you of, oh yeah, this was this satellite passing through. But if you plug that all in and Heavens Above doesn't know what you're talking about and it doesn't know what object you saw, there's a chance that you just tracked a piece of debris that is either untracked or isn't reliably tracked. And so there you could probably report it to the NASA Orbital Debris Program Office. They have a handy contact us link on that page, and you could go and say, hey, I was out at night, I was taking pictures from this location pointed in this direction, and I saw an object move in this way. That little bit of insight, that little bit of detail could be the difference between predicting a conjunction event or missing it. So, what are conjunction events? Spacetrack.org is run by the 18th Space Squadron, and they helpfully produce these public reports of all of the possible conjunctions. This data set is, only readable once you analyze it a bit, but there's three categories. In the first one, you have general information like the timing. Importantly, this collision probability chart tells you what's the probability of collision. So you can see for these examples, fairly low, 0.017% chance of a collision. Over here, you can see what debris was the first object. It was a piece of small debris. And what piece was the second object? It was another piece of small debris. Interestingly, it was Cosmos 2251 debris. That's a piece of debris from the 2009 Iridium Cosmos collision. And on June 19th at 1:39 p.m. UCT, or that was when it was created, sorry, at 4:55 p.m., they got close to each other. And this is happening over and over and over again. Looking at the whole data set, going back the last 30 days, there were 3,684 of these conjunction reports. Of those, 303 were greater than a 0.1% risk. Now, that's not a huge risk. Many of us take risks higher than that on a daily basis without really even thinking about it. But the concern is that this is happening every 30 days. There's a new batch of hundreds of these objects. And so the math is not, oh, what's the chance that the 0.1% odds occurs? The question is, how long can we go with 99.9% chance of nothing happening again and again and again? It's a weighted coin that we're flipping, but it's very odd that it's going to continue to land on heads. One final concerning part about this was of these, 1,826 were debris on debris, a conjunction in which neither party has an ability to move. We're just crossing our fingers and hoping. Or we would be. This last chart this is a pretty cool thing that shows you the next 15 minutes, and it demonstrates in a pretty cool way distance between two objects. And so the steeper the line is, the faster that relative conjunction is. So these green ones are objects that are coming together and docking, but these bright red pillars are objects that got very close, but then flew by each other. So, one more point, legal concerns of the Outer Space Treaty. So we have this problem. Clearly, we need to solve it. Clearly, we need to do something about it. So what's stopping us? Well, that same Outer Space Treaty that we all signed after 1962 and the nuclear test where we said, whoa, this is crazy, it presents a few problems in the modern day. First off, it defines ownership as belonging to both the nation that you launch from, the nation of the company that launches you, as well as the nation of the company that runs the satellite. So there's a triple threat here of if I need to get rid of a piece of debris, I need to go ask the nation it originally launched from, whoever originally launched it, as well as the operating company of that object back when it was operating. Not every nation still exists. Some of them have changed names, some of them have changed territory. Definitely not every launching company or launching organization still exists, and many operating companies have been absorbed or gone bankrupt or just disappeared entirely. But the Outer Space Treaty still says you have to find the path of responsibility and ask for permission, or it's an international incident. Also, if your satellite is fully uncontrolled, is that the same liability as someone taking your satellite, putting it on a deorbit path, and then it runs into the ISS. You're trying to be responsible, but in acting, do you now have a higher responsibility to ensure no danger? This one is a personal gripe of mine. The current statistics says that with all the debris re-entering and this increase in the population of debris, over the next 10 years, there is a 10% chance that there will be one fatality on the ground from orbital debris across the entire world. That is terrible. We do not want anyone to die from just a piece of steel falling out of the sky. At the same time, and this is me being a pragmatic, I have a teenage daughter, a teenage foster daughter who is learning to drive. The risk to the world of her getting on the road is higher than the next 10 years of debris re-entering the Earth. So when this is brought up as a concern of, oh, we shouldn't, whoops, I stood too still for too long. There we go. As we look at the concern of orbital debris and the impact it could have on the world, there's the saying of, oh, we shouldn't deorbit it, it might hit something on the ground, is a little overblown in my opinion. It's not a risk that we can ignore completely and we should do due diligence, but we also shouldn't be afraid to try and clean up our mess to some degree. Yeah, there's not much of a difference between destructive and non-destructive. Some countries still think blowing it up counts as removing debris. We got to work on that one. And then Article 3. So in the Outer Space Treaty, there's an article part of it that says basically we all have to be good stewards of space. Is leaving your debris being a bad steward of space? And does it justify me going up and removing it without permission? That's a hard one to answer. One notable case is that Russia never claims that its satellites have broken. Cosmos 2 is just as active as Cosmos 2251 because that's how they like to do it. So even though they are very old machines and we're very sure that they're no longer operating, if the owner says that it's still an active mission, are we in the right moral position to go and remove it? And finally, the operating nation versus the host nation of you now have international conglomerates of companies that are founded in Singapore and they have bases in Japan and America and Switzerland and they launched from New Zealand and just this mess of responsibility. We really should clean this up. Just get the whole world to work together. That's pretty easy. So as we try to solve this problem, there is something that we learned very early on from a study done in 2011 by NASA that gave us hope. I apologize for this talk being, 30 minutes so far of a little bit scary and a little bit depressing, but there was hope, which was this study that said, okay, back in 2011, we were at 13,000 objects in space. If from that point we did 90% effective post-mission disposal, 90% of missions said, okay, we'll get rid of ourselves at the end of the mission. That would be the red line. Still going up, still increasing, but now more kind of linear. If we added that starting in 2020, we would remove 2 objects a year. That's the blue line. Still going up, but hardly at all. And if we remove 5 objects a year, that's the green line. I look at this and I think it's analogous to having student loans. If you don't pay your student loans at all, you just ignore them, you're the red line. You're going up and to the right, and exponential growth is just going to ruin your life for the rest of your years. If you pay everything all at once, if you just go hard and say, I'm throwing everything into student loans, you're the green line. You're paying it off in a reasonable time. If, though, you can only manage just your interest payments, if that's all you have to spare, but you decide to put it towards it anyway, you're the black line. You're not getting rid of the problem, but you've stopped it from growing uncontrollably. 5 removals a year. That's what it would take to control the orbital environment. The rapid growth, the exponential danger, that is all because no one's doing anything. No one is removing their debris. You go and remove the 5 worst objects, you've just bought another year of time. And you do that consistently, and you have now stabilized the environment. It's a scary story. The risk is very real, and there's a chance that we don't meet the challenge and we do kind of ruin space for the future. But it also would take just a little bit of action and a little bit of attention in order to resolve this problem and give us a fighting chance for the future. So that's where KMI was founded. We said, okay, let's do something. Let's solve this problem of how do we remove an object from space. If that's something that can't be done right now, let's make it something that can be done. So we started planning out our mission. We planned out what would be needed. Well, you need a spacecraft. Okay, People are making spacecrafts. There are companies that want to make a spacecraft. They have a standard design, they'll charge you a standard rate. It's pretty nice. Well, that spacecraft needs power. Okay, solar panels. People make those. It needs propulsion. People make that. It needs navigation and star trackers and GPS. Yep, people make those. Turns out almost every part of this spacecraft that we need to remove debris is already being made. There are already companies that mass produce these satellite components. It's no longer the 1960s. It's no longer an activity for just nation states and budgets in the billions of dollars. It is an activity that you can go on an online catalog and order your parts and assemble your satellite all your own. There was just one aspect missing. How do you grab the object? We sketched out the plan, we sketched out the ConOps, and we said, okay, we can get right up to the target. We can approach, we can be right next to it, but how do we actually hold on to it? That became our white whale. We said, okay, this is a software problem. It's a hardware problem. It's a business problem. The hardware is the hard part. Let's solve that first. And so we developed Reach. You can see it in that GIF up above or in the images, this tentacle monster idea that unfolds. We really wanted a design that would wrap around any geometry. We didn't want to be stuck building a separate end effector for each and every object based on its shape. We wanted a design that would fit around anything. I'm happy to say that in 2024, we launched that design up to the International Space Station. We were able to demonstrate in microgravity this concept of a remote microgravity grab onto an object. This video brings me a lot of joy because a few years prior, I had the privilege of meeting a very famous astronaut who, for his sake, I won't say by name, but I told him about our mission. I told him about our idea. He looked at an early drawing and said, well, don't mean to burst your bubble. I've been in space. I've been up there. I've had to, grab wrenches and screws out of the air. That's not going to work. It's not that easy. It doesn't work that way. You haven't thought about all the problems. It's just not going to work. And so having this video, which is just one of 180 captures we were able to complete while up on station, is great evidence to the contrary. It does work as you understand the conditions around it. And that's what we did. We collected a lot of data, we understood the mission, and we're working now to implement the changes that will give us that universality that we need to solve this debris problem. Oh, that is a link to Instagram. I'm not sure why that opened. I think, so this is, hey, cool. The ISS is Instagram that has nearly 1 million likes. That's a cool thing to throw up here. The ISS Instagram does not get this many likes normally. This was a surprise to us because they were very clear to us of, no, you can't possibly post images with astronauts in it. You're not allowed to do that. And then on December 10th, NASA goes, look, we posted your image of an astronaut doing your experiment. People love it. So that was a fun insight. Thank you, NASA, for that one. Really appreciate it. Let me see if I can. Well, I've got this bar in my way, so let me stop sharing for just a second. I'll be coming right back. There we go. Okay. Okay. So, KMI's mission now. We have built the end effector. That's reach. That's our ability to grab onto the object. In the process, we discovered a product called Asteria. This is taking our same technology, but instead of the idea that we want to grab and later release the object to deorbit it, what if we want to grab and stay stuck? Put a transponder on an object so it's easier to track. Put a very small deorbit thruster or a deorbit balloon or drag balloon, something like that. So Asteria is the product that would allow us to do that. TumbleEye, the software solution, we did eventually get around to that. The ability to look at this tumbling debris object that we've never seen before, pick out key features, and then track them as they tumble to identify what is the shape of this object and how do we want to grab onto it. And then all of that combined into our LAYLAP spacecraft. This concept of a delta V monster that is able to fly around with 4.5 kilometers per second of delta V, going and grabbing on average about 4 missions per spacecraft. The customer base for this is pretty interesting. They have a problem of debris in space. Funny enough, for the constellation operators, that debris is mostly their own fault. When they have a constellation of perfectly organized satellites all crisscrossing each other in different inclinations, and then one of them starts to have a problem, so they move it out of the way, that movement failed halfway through, And you end up with a periapsis below your constellation, apoapsis above, and now every 90 minutes it's crossing through their constellation, causing all kinds of trouble. That has happened many times. And if I had $10 million for each time it happened, I'd have a business. So the the purpose of this has become commercial. We can solve a debris problem for a commercial interest. But the real value is that as we get better at this, as we improve this technology, the cost comes down. And as much as saving the world should be priceless, we are seeking out what is the price at which saving the world is no longer this, egalitarian extra on the budget, but it just makes sense. It's just the thing you do. So, what does that future then enable? If the future is not the one I was talking about at the beginning of fire and brimstone, of debris clouding up our atmosphere and preventing exploration of space, what could it be instead? Well, it could be outposts. It could be travel to other worlds. It could be a free exchange of material and people to and from Earth, not worried about this hazard race through the debris field on their way to and from. Could be vacations and family. Safety in space is not just about improving the technology of the rockets to ensure that they're safe, but it's also about improving the journey and the journey out there being safe from micro debris impacts. The one that I'm most excited about, manufacturing in space. This concept of the debris in space isn't just trash. It's material. It's aluminum, infinitely recyclable. It's electronics. It's advanced components, and it's already in space. No matter how low you get the cost of launch, something in space doesn't have to pay that. It's already there. And so there's a beautiful future in which we are able to collect the debris in orbit, and rather than send it down to the atmosphere, rather than burn it up, rather than risk that very small chance of immortality, we instead keep it in orbit. We gather it together, and that becomes the foundation of factories, stations, hotels, hospitals, what name you. Personally, there's also some very cool technology about the microgravity environment and how you can manufacture crystal structures and other such things, human organs, synthetic human organs, to be clear, that you just can't create on the ground. There is a vibrant possibility of the future of space being industry that is serving humanity in a way that can't be replicated anywhere else. But to secure that future, we have to solve the debris problem. So that was my presentation. I think I did pretty good on the 40 minutes that I was given. Excited to take any questions that there may be either right now, or you're welcome to email me at adam@kallmorris.com. Love to talk about this. Again, I went a little bit data heavy on this, but truthfully understanding the problem, the solution is right there with it, and it's progressing every day. So excited to share with you what we've been working on, the situation overhead, and excited to hear from you about any ways that debris has impacted what you do or ways that you think you could help. I will call out one example. I see Pat Seitzer here on the call. He has helped us in the past with the question of whether an object is tumbling is one that can maybe be answered by how it reflects the light from the ground or from viewing it from the ground. So thank you all for your time, and happy to take any questions.
Yes, Doug.
I may have forgotten, but you laid out a distribution by orbital height. Did I miss distribution by size? Your device is going to be for large. What is by size debris up there?
So that cut out a little bit for me, but it sounded like you were asking about the distribution by size. So you did not miss it. I did not include the distribution by size. The main culprits for the largest debris are definitely the rocket bodies. There are a few operational satellites, for example, oh my gosh, I'm blanking on. Oh, NVSat. The European Space Agency has NVSat, a giant 8,000 kilogram satellite that they launched. It was supposed to be a 25-year mission, and after 9 years, it failed. That's unfortunately for Europe, they're one example of really bad debris, but it's really bad debris. That's one of the biggest objects out there. The rest of the large objects tend to be rocket bodies. And so where they show up is that they're on this chart. They actually show up in the 1400 to 1500, but that is not where it lives. Again, semi-major axis is an average. Those rocket bodies were used to boost satellites out to geostationary orbit. So they're on this elliptical path that is doing some kind of trajectory where it brings it way out and way back in at very different relative speeds. So we need to solve that problem for sure, but there's also quite a selection of rocket bodies here in low Earth orbit for us to grab, and they're scattered at about the same distribution as the rest of it. They don't tend to exist in the lower altitudes just because they have a larger cross section, so the drag slows them down a little bit faster. So, go ahead.
Nuts and bolts, small objects. Are
Oh,
Don't talk, so we'll just talk more. Oh, is there debris that's very small? And what's the distribution? You know, like literally nuts and bolts that have broken off, or after that collision, all those small pieces. What's the distribution of that?
that's a great question. So I probably could find it if you gave me a second to search. So the group that did the simulation of the 2009 Iridium is called, oh, what group is that? It's either AGS or AIS. They do a lot of calculations like that. These numbers of the space track numbers, they only go as small as 10 centimeters, about the size of a basketball. So 10 centimeters and up is the 47,000 trackable objects. If you go 1 centimeter to 10 centimeters, that's about 1.1 million more objects. And if you go sub 1 centimeter, that's about 100 million more objects. So the tiny debris is very prevalent. The 1 centimeter to 10 centimeter is quite concerning because it's hard to track that. But the largest debris is what is the primary target, because if that gets hit by another piece of debris, even a small one, it becomes thousands and millions of small pieces itself. So I was once talking with a colonel for the Space Force who was asking me, oh, I don't care about the big debris, I care about small debris. How are you going to remove small debris? And I said, sir, I will strike you a deal. I'll remove 10,000 pieces of small debris. They'll just all be in, one clump when I do it. Because that's the logic of removing the large debris.
Do you have any future plan on removing smaller debris, and have you ever considered using magnets in collecting debris?
Let me think about that for a second. My role at KMI, as KMI grows, is going to evolve. And I am probably going to end up in the group that's not thinking about how to perfect the operations of today, but perfecting the operations of 10 years from now. We will need to solve the small debris. It comes after solving the current problem. And the way we're going to do it is not something that I have a good sense of. Magnets are something I'm aware of, but they also come with a lot of drawbacks. There was a startup that I once talked with that had an idea for could not even describe it to you. It was stellar wind vortex over the poles that would draw down small debris. And I wish that I understood what he was talking about, because I feel like I would be 10 times smarter if I did. But it's a problem that must be solved, but it's one that becomes easier to solve if you're able to build the infrastructure. So that was what was apparent talking to some people. Building the in-orbit magnetic station or magnetic rails or whatever, those are large pieces. And if you have other pieces flying around threatening them, it's going to be harder to establish the necessary number. So we took the approach, large objects first, then small objects coming after.
Well, I've got a comment and a question. Comment on magnets. Spacecraft generally made of things like aluminum, titanium, lightweight materials that aren't magnetic. So if they made them out of steel, that might be a good idea, but I doubt it would be practical. But the question relates to the energy requirements to get stuff deorbited. The amount of energy it takes to change an orbit of something is comparable to the amount of energy it takes to get it into that orbit. So how are you going to actually move things into orbits that will allow them, to fall to Earth gracefully without having your carrier satellite itself go into the same orbit and fall to Earth?
I believe I caught all that towards the end. It trailed off just a little bit, and I don't think I caught the last few words, but it sounded like you were asking about how to deal with the fact that changing inclination and changing orbits takes an immense amount of energy. So how do we possibly collect everything? How do we bring it together? If if that was correct, so if you look at the distribution of all the objects, and our spacecraft has the delta V to efficiently move plus or minus 3 degrees of inclination, that 6 degrees of range actually allows us to cover, what was it, 90 over 95% of the objects in orbit with 17 buckets. That's more buckets than I would like. It'd be convenient if they were all in one place, but it is a number that can be achieved. 17 orbits that we have to launch into, and we have global coverage of the debris. Now, that does mean that we're not going to bring all debris together into one place, but there's currently, as I believe ESA estimated it, about 10,000 metric tons of debris in orbit. So we don't need to concentrate all of it in one place. We can have 17 factories. We can have 17 installations where we are collecting the debris and operating on it in slightly different orbits. So it's a problem of that energy to change orbits is certainly true. There's a couple of unique ideas about building a glide craft to bank in the upper atmosphere and change inclination rapidly. But before all of that, it is a finite number of buckets we have to fill, and we do have the technology and the capability to fill them with spacecrafts and collection stations.
Are objects that are dead but all the way up in geosynchronous, are they relatively safe at this point because they're so far away, or there relatively few collisions up there, or do we have to start worrying about them as well?
I would say that geo is of concern, but because you don't have as many crossing inclinations, everything's moving at around equatorial, you end up not having this kind of cascading effect. The main problem with geo is that there is one orbit in geo that is over, Panama. There's one orbit that's over the west coast of Africa. And so if you have a satellite there that dies, that slot is now taken up. And that's kind of the problem we're running into is almost every slot is taken up by either an active satellite or a dead satellite. So that one is a bit of a commercial interest, not from the standpoint of, oh, we need to protect ourselves from this imminent danger, but more so we need to free up that orbit. And so there's a business case there, but it's not our priority because the situation is not stable, but more stable than the LEO one.
Any other questions? Zoom audience or in the room?
I did see there was a question in the chat.
Oh,
So debris collection work, manufacturing. So debris collection, just to answer that, catching things is really not a valid strategy. You run into the problem very quickly of trying to catch something moving at 17,000 miles per hour. It's just going to make a hole in your net. So you need to go and collect objects and manually bring them to the station most of the time, at which point the economies of scale tell you grab the largest objects. So the manufacturing is less about taking a bunch of small pellets and combining them, and going to be much more about taking a large rocket body and disassembling it. So the good news for those who like sci-fi, very good justification for humans in space. I can very easily see a future where we have an Expanse-like spacecraft or space station with engineers on board with cutting tools and welding torches ready to rip apart a piece of derelict space history in order to create, the next space station, the next module.
Would aerogels work better than a net?
That is a great question. The aerogels I'm thinking of do have interesting properties, but I believe they had a brittle property as well. And that's the main thing you're trying to avoid, is any sort of brittleness. Just as a quick example, there was an ISS study where they wanted to track, what was the amount of that small debris. And so their idea was, let's put out a square meter of like tin foil, essentially, and have a camera shining behind it so that when we point it at the sun, and we get the specks of light coming through, we can count how many dots there are. And it was supposed to be a 2-year mission. And after about 7 months, there were so many holes in it that it had shredded the tin foil, and they had to report on it as the amount of debris is substantial.
Any other questions? Comments?
Charlie, I have a question.
Has
Norbert.
anybody been hit by space debris? Okay, Norm, go ahead.
No mentions made of the exhaust and fuels of orbital adjustments and that kind of stuff. How much of an effect will exhaust leaks from fuel tanks and that kind of stuff have? The erosional characteristics, you say a fleck of paint causes severe damage. What about expended gases and so forth?
So definitely those incredibly small particles that would come out of expanded, like a thruster where it actually fires and there's combustion, that essentially soot, the very fine soot that is resulting from that, does have an impact. We do know that paint in the long term up in orbit actually ends up with this crackled feature, and we think it's from just a ton of these tiny elements piercing through. The interesting thing is that, if you fire the engine, the relative velocity of the exhaust tends to be at a much higher speed in the opposite direction. So if you are increasing your orbit, it's typically enough that it's actually going to deorbit quite quickly. It's going to be on a re-entry path. If you're going in the other direction, it's sometimes fast enough to put you, if not on an escape velocity, a much higher orbit where it's less of an issue. For the expanding or escaping particles, there's an interesting example, which is the one case of debris that KMI cannot capture. We just wipe our hands of it and say, not with this design, it'll be its own special mission, and that's the coolant bubbles. So some of you might know this because it's often used for training the radar and kind of focusing them in, but Russia had a couple rocket bodies that had radioactive liquid coolant in them. And when those rocket bodies were left in orbit floating around, the coolant ate through the skin and seeped out not in a pressurized way, but in a complete way. And they now form a perfect sphere in orbit. So it's great for training your radar. We actually talked to a group that was like, don't remove that debris. It's actually beneficial for our purposes, but it is just a floating ball of coolant. And it will have just as much impact as anything else if it runs into it, but it's very hard to grab onto. Our octopus arms are definitely not going to work for trying to grab a ball of liquid radioactive coolant.
But just a comment relative to that, that I learned about when I was at JPL back in the 80s, is that one of the biggest problems they have up in space is with high energy oxygen. Those oxygen atoms hitting things at orbital velocity just does tremendous corrosive damage to surfaces, and that has a lot of spalling things off. So any gas hitting the surface at high energy, I think the estimated kinetic energy is something like 5 electron volts, if that means anything to you guys, but that's energy enough to do chemical reactions. So these gases in orbit can be just as bad.
Yeah, atomic oxygen degradation is definitely a concern for our mission. And it's part of the reason why we want to operate at the higher orbits and avoid going down into the atmosphere, because you don't have to be at 100 kilometers to suffer severe impacts from that. That atomic oxygen is still, in fact, a feature. I don't think it's all the way up to 2000. I think it does drop off and become more of a probabilistic problem by that point, but definitely down in the, up to 800, I know for sure it is a increasing problem. One advantage for us is that by being up there to grab objects and remove them relatively quickly, we don't spend a lot of time in space. Our ideal mission is 6 months or less before the spacecraft is out of fuel and deorbiting itself. So we do get a slight advantage there of having to worry less about atomic oxygen degradation and things like radiation damage to our electronic components. So thank you for bringing that up. Very important, valid point, and definitely just space is a harsh environment. I think people say that and they don't really appreciate it, that the vacuum is not empty, and even if it was, it's still a very harsh environment.
Is it practical to have launch vehicles and the payloads go up without any paint at all? For instance, are there materials that can be part of the body that won't just flake off?
I would suspect yes. I'm speaking a little bit out the side of my mouth right now because I haven't studied this extensively, but I believe the atomic oxygen degradation is mostly affected by elements which can oxidize. So, aluminum has this problem of getting oxidized by the atomic oxygen essentially ramming itself in. But if you throw up something that is less reactive to oxygen, for example, I think the gold plating on the Mylar is specifically chosen because it's less reactive and going to suffer less damage.
Any other questions, comments, input?
Just one other comment, Charlie, if I may, the notion that you could almost write a science fiction nightmare of trapping a civilization on a planet by purposely orbiting debris, billions of objects to trap a civilization on a surface. I haven't seen any Hollywood movies to that effect. But as we go further out, like say go to Moon or Mars, are we really risking a lot when we go through the gauntlet field, those orbits that you mentioned? What are the likelihoods of a spacecraft leaving Earth orbit running into that stuff?
Right now, a change that has actively been made is that launch windows are much smaller than they used to be. We have to basically time it to be in between debris. And so sometimes when a mission has an instantaneous launch window, especially one that isn't rendezvousing with the ISS, sometimes the cause for that is because they had a very narrow calculated window through the debris field. And when they missed that, it's not that it's completely unsafe, they just haven't been able to run the calculations. So that is one immediate noticeable effect, and not every time, but sometimes. In the future, a Kessler syndrome type event, when it hits that exponential curve in the hockey stick and just really becomes unstoppable, that's when taking off would become dangerous. But even then, traveling through the debris field, kind of that instantaneous of you're going from A to B and the debris field is in between, that's always going to be safer than trying to place a satellite that lives in the debris field or crosses it at a different inclination. So this risk will undoubtedly increase. And there are some sci-fi novels that highlight, this sci-fi Earth with space travel and commercial liners. And typically they like to use space debris as as a convenient plot device for, oh, you have this commercial liner and suddenly it's no longer safe, it's now in danger. And that's quite realistic for what could happen in the future.
Any other questions?
Well, you scared the heck out of me.
Doug Nell is going to have nightmares now.
Well, you can also dream about the Laylap spacecraft saving the day as well. That's the one that keeps me resting well at night.
Well, you did earlier in your presentation, though, give us something that we can do to help as amateur astronomers, because you gave us that link where we're going to report something that, say, went through one of our photographs and we can't find it, or identify it. Could you email me that link so I can send it out to the club?
Absolutely. I'll send that to you right after this.
Yeah. All right.
So you want to get the Evans above and also the one at NASA. So the one to check whether it's no and the one to submit.
Yeah.
Right. Yeah, if you could send those with a little bit that we can help. So. And then one other thing, just to show our appreciation for our presentation, we would like to give you a club t-shirt or a baseball style hat, whichever you prefer.
Thank you very much. I would
a
appreciate the
couple people.
t-shirt.
You'd like the t-shirt idea? What size?
I will take a large.
Okay. If you could just send me an email address, I'll probably have that shipped to you from Traverse City.
Wonderful. Sounds great.
Okay, cool.
I think we have a non-debris version.
Give me the one with the holes in it. Say it was from space debris.
Yeah, I love it. Okay. Yes. Very, very good. Appreciate it, Adam.
Thank you all. Thank you all for your time. as I am not an official member of the club yet, I am going to drop off before you get to the business conversation. So
And I
thank
did
you all for your time.
I did catch the yet. Okay. So, on reports, I just want to remind everybody, we have open houses both tomorrow and next Saturday. As it turns out, I did get enough volunteers that I think we can run the one tomorrow night. So I'm gonna wait until morning because the way my luck's gone this week, I don't trust doing it right now. But as soon as I get up, unless the forecast has changed, I'll go ahead and send the notifications and stuff that we will go ahead and do it. Either Jack or I will open the gate at, let's see, sunset is what, 9 something?
And
Yeah, so probably 8:30, 8:15, something. I'll send it out. I'll figure it out, so. And then I'll turn around and start looking for help for next Saturday. In fact, somebody did respond and said they couldn't help this Saturday, but they could next Saturday. I just have to see who that was, but we'll need more than that, so. We are still looking for a webmaster. I did send that email out and announced at the last meeting, but we've had some people volunteer to help, which is good. Jeff's already had some communications with them, Krishna, some communication, so we're getting that part, but we want to actually fill that webmaster position too. So if anybody would like to do that, even if you're questioning a little bit, then you could talk to Krishna or Jeff and they can, determine how much, yes, exactly. Yeah, how much we need to help and everything so we can get you up to speed. So please consider that. If not, we'll come up with some kind of a draft process and you don't want to do that, so. But again, please consider that, or if you know somebody that might be, see if you can talk them into it. And I'll probably send another email because we do want to get that fulfilled. And then one other thing I got from the Night Sky Network. I'm getting so much of this stuff, I'm gonna have to buy a new place to store it all or something, but I don't remember what it is. Oh, some things about the Solar Dynamics Laboratory and stuff. I guess this is because of maybe Solar Maximum coming up. Some little card things, solar glasses, but then the main thing seems to be
that look good here.
yeah, I wonder if we should see if Austin can use it. Yeah. I'd rather here than our observatory where it'll rot out and not be seen very much. That's also true. Yeah.
Let me turn.
Yeah, yeah. Yeah, what poster on the wall? Click. Okay, good idea. I'll ask Austin about it. So anyway, yeah. Even some Velcro ties to help hang it up. Brilliant idea. Thank you. Okay. Actually, that's all I had. So Jeff.
Yeah, Ed Hernandez was one of the web volunteers to help with stuff. I've gotten him permissions and elevated him to there. He's going to start looking at some of the blank pages, especially at the young Jack tonight. Oh, yeah. Tonight Jack emailed me something about the new calendars that go on Young Astronomers, and I figured that'll be a good time to get Ed indoctrinated into where to put those and whatnot in the new site. In the old site, they basically don't have anything that doesn't require a U of M login. So U of M folks need to take care of that, which I can do. It doesn't take long. I don't remember the other individual that volunteered, but I know Doug Scoble, he was going to expand some of his responsibilities, which sounded great to me. And the other person, I can't remember. I apologize for that. The other little bit of news is the university, and this is, I don't know how widespread this is, but ITS, they have their meetings and on Tuesday and Wednesday. They are looking to
they're looking to consolidate their authentication and authorization tools into a single product. Right now, the university has got a whole collection of piecemeal stuff that it actually works together and it's remarkably stable, et cetera, but it's individual pieces that weren't meant for each other. So they're going to consolidate this thing. The go ahead or the go light or whatever is November 5th. So sometime between now and November 5th, they're going to be migrating all kinds of services over to that. And what does that mean to us? That means probably our web authentication on the old site and the M community lists that we use for our emails. So the emails will probably get migrated, but we haven't heard anything from ITS, even for official university sites or the others. So that's something that's coming down the pike. I'm going to be watching it pretty closely and asking the folks who are implementing it what they're going to do about what is it? Affiliated groups such as the Lowbrow. So that's my little bit of IT news. Charlie, it's back to you.
So what I'm working on right now is this telescope was donated to the club by Dr. Watson. It's an apochromatic refractor and has a ZWO setup. So it has a ZWO mount and tripod and the 107 millimeter aperture refractor and a bunch of miscellaneous pieces to go with it, cables, an ASA air or ASI air thing to help run it. And I'm trying to put that all together and hopefully I'll have it at the open house tomorrow night. We'll see if we can make that work. Other than that, nothing else.
No report. Oh, yeah. I just take out. That's a microphone.
I just have a quick question for Jeff, and it has to do with this internet that they talked to us about bringing it out to the observatory. And it's something that I know we talked about before, and then they stopped doing it, but they've contacted us again, and there's been some discussion. So I'm just wondering if Jeff has any update on that at all.
I haven't heard anything from them. I think I'm on the same email chain as you are. So
Okay.
we see it, we probably see them together. But ITS moves a little slowly, but they were talking, the last email was next month. They're supposed to gather their.
Sometime, yeah, in July or August. That's why I was wondering. Okay, it's.
The shock when they said they were gonna roll out in November. It's like, really?
Yeah. That's all I have to bring up.
I don't see any other officers. I don't see. Does anybody have anything else?
We have no report.
Correct.
Charlie, I've got a couple of little tidbits, if I may.
Yeah, go ahead.
Well, first of all, happy summer solstice to everyone, tonight. Yeah. The next meeting, look forward to seeing everybody next month at July at the planetarium. There's a 11 a.m. Monday is the first images of the Vera Rubin telescope. And you may have seen an email from Shannon Murphy about the venues where they're going to have sort of gatherings. They call it a party. I don't plan to have a kegger, but
Darn it.
I know, but it should be interesting if you're interested in stopping by either our planetarium or the two venues on U of M campus. I'm sure they'd appreciate folks being there and enjoying the shows. We're not sure what we're expecting to see, but I was talking or at least emailing back and forth with Artis Harold, who was their educational supervisor on their project. And she said that they're going to release the images about 11:30 a.m. on Monday. So the show starts at 11 a.m., but it'll be about 11:30 by the time they get the images up online for folks to look at. But until then, it's a closely guarded secret as to what they're going to reveal. But just giving a heads up for that.
Thank you, Norm.
So Charlie, this is Adrian. I've got a couple items. One, I'll be heading to Astracon next week. It's from Wednesday next week through Friday, and it'll be at Bryce Canyon. So it'll be a bit of a drive, but I plan to head out there. Also, I will be handing over the Causland Coronado 60, as we talked about in emails, to Doug Scoble. He's going to be in Ann Arbor, so it's going to make the exchange pretty easily. And he's got a mount for it, so he'll have the scope with a Vixen dovetail plate. I'll hand him the eyepiece. I'm sure he's got others. So Doug Scoble will be the new custodian of the Coronado. I took one last look at it and saw the giant sunspot group that was aimed our way a couple of days ago. Doesn't look like it erupted during that, but the views are still good. So apparently I haven't broken it in a couple of years. It's been to Okie-Tex. It's been wherever I've gone to do solar stuff. But so it's a nice scope. You give Doug some time, and then if any other lowbrows are interested in renting it for a little bit, you'll be able to inquire with Doug. And from there, go from there. At this point, John's mount just was no good. So if you have a mount you can put the scope on, it'll be better as far as being able to use it. But Doug gets first dibs. I don't know if he's here. I didn't see him out here with us in virtual land, but at any rate, um, that's all I got. I'm still overcoming a cold, or else I'd be there to eat pizza with you guys.
Thanks, Adrian.
Adrian, when's Doug Scoble coming to town?
July 7th. Sounds like a good opportunity for pizza to me.
Yeah.
And Norm didn't mention, by the way, the July meeting, if anybody didn't know or haven't been there before, we have pizza and pop and cookies and everything that we eat before we get the meeting started. So just an extra reason to attend that one. And it's over in Eastern Michigan. So we'll meet, do that first, then we go into the planetarium, have the presentation there. Norm usually has something he wants to show us. And then if it's clear, and even if it's not, probably we can walk over to Scherzer Observatory and see all of Norm's toys, tools, and tell us blur out, we'll actually use them. So anyway, it's a very, very fun meeting. So I'd like Mark. Norm. Request.
It's Ted Sirkovsky. I have a couple of things too. One, is there such a thing as astronomers' bucket list? Summer is coming, people are traveling, there are places you just drive through and it's worth of going off and seeing. And for me, I'm new to this thing, relatively new, and learn on the road, but just all those heads coming together. Maybe, everybody has something different and we could put on a list or on the website, everybody could use.
It's like we do have a section on the new website for, I think it's, I forget what I called it. It's observing locations. And we've gotten submissions from people about what amenities are there, good places, little tips and all that for where to locate and whatnot. I've got a private list of places that I like to go to, but I haven't written them up to put on there. But people have got suggestions like that, feed them to me and we'll get Ed or Doug or somebody to, put those things in, or myself. So we're trying to accumulate that kind of a list for observing locations.
So the places like telescopes you go and see, like last month was a presentation of this telescope society in Vermont, I guess. So, and I'm going, like next week in that area, I'm going to make that trip. I didn't know about this before. So second thing is, happened to me twice. I had my rig set up close to my tracks deck, and I ESD charge, and I discharged myself twice to my telescope and smoked focus. The same brand, the same device, so it's something, I assume something wrong with the device, but are there any like guidelines or things you would do? I mean, you know.
Trek, so I'm kind of interested. No, I hadn't heard of that.
Try to get a ground that you could turn.
Yeah.
Like get a ground someplace that you.
Yeah,
can-
before touching the scope, yeah.
Touch the ground.
Yeah, but then, you know,
Work on
yeah.
Server hardware all the time and I'm always grounding myself for.
And I'm electrical engineer and like,
Oh, so you-
I kind of, and they paid me to fix it before. Yeah, I mean, how practical it is doing that at night and, you know.
Yeah.
Your equipment, Howard, you have an extension.
Yes.
Make sure that your outlet is properly
Yeah.
grounded. That could
There
be
you
a
go.
problem. That
Yeah,
you-
that's
Make sure you got like, you know,
Yeah.
GFI on the circuit for protection.
Yeah, it is.
Grounding is all good.
Yeah, but so, but still, I guess I would need to have another strap going from the telescope mount, I guess, to the ground or putting a mat or, yeah.
I really have to look at it to see that I've had some digging into grounding issues and how do you. All that sort of stuff.
You don't want to just get them done.
Oh.
You forgot it by now, right?
No, Norm brought up the Vera Rubin watch parties. On the campus, they're ticketed. They're at the planetarium, with the Natural History Museum, and here. And you have to apply for the tickets online. They're free, but there's only so much room in each venue.
Good. So you can't just walk in.
No, I don't think so. Austin probably has a pretty good idea of what's going on.
The email I saw today is they're all filled up.
Oh.
Who's that? Hold on.
Well, if anybody here is interested, I do have an extra ticket, so.
And the price for that?
Anybody got anything else? Anybody in the Zoom audience?
Nope.
Well, in that case, do I hear a motion to adjourn?
Motion to adjourn.
All in favor? Okay, thank you very much. See you next month. Have a good 4th of July.